Hi there, Mr. Sutton here, bringing you the BC Calculus Chapter 7 Quiz 2 review solutions on Taylor series and error bound. On this problem, they want the third order Taylor series for f of x equals ln of x minus 1 about x equals 2. So this is not a Maclaurin series, it's not centered at 0. So we use our more general nth term formula of nth derivative of a, which is 2 in this case, x minus a to the nth power over n factorial. So this formula here, pretty much just a Maclaurin series, only we have an x minus whatever your center is, and we have to take the derivative at the center rather than 0. So this is going to start us with the value of f of a, whatever that is. Then we'll have f prime of a times x minus a, followed by f double prime of a, x minus a squared over 2 factorial, and so on and so forth. So this means we're going to need to figure out, if we want third order, we need the first 3 derivatives of this function at x equals 2. So let's start with just f of 2, which is just going to be ln of 2 minus 1, or ln of 1. ln of 1 is just 0. So f of 2 is 0, and we're not actually going to write anything for the first term of this series. For the next thing here, we need f prime. So that's going to be 1 over x minus 1, or x minus 1 to the negative 1 power. I'm going to write it like that, just so it's easier to take more derivatives. And we're evaluating that at 2. So this is really, let's see, 1 over 2 minus 1, so 1 over 1, which is just 1. And we're going to just keep getting expressions that have this x minus 1 parentheses, which is just going to come out to 1 every single time we plug in 2. So it's really going to be whatever the coefficient is that determines our derivative. So moving on then to f double prime of 2. That's going to be, let's see, negative all this stuff to the negative 2 power, evaluated at 2. And again, this stuff inside here just comes out to 1, so it's really just negative 1 when all is said and done. Then finally, f triple prime, because they said third order, that's going to be, let's see, positive 2, x minus 1 to the negative 3rd power, evaluated at 2. And this comes out, plugging in 2, this comes out to just 2. All right, let's write out our series at this point. So f of a, that was f of 2, that's 0, so no need to write that. F prime of a was 1 times x minus whatever the a value was. Well, our a value here is 2, so this is just x minus 2 that we can write initially. And then we have the second derivative of 2. So that's going to give us negative 1 times, let's see, this will be x minus 2 squared over 2 factorial. And finally, using our third derivative, we're going to have 2 times x minus 2 cubed over 3 factorial. And that's our Taylor series. For this problem, they want us to show, using the alternating series error bound, that a 5th degree Maclaurin approximation of f of 0.8 for sine of 2x is within 0.009 of the true value. Okay, so we have this Maclaurin approximation using sine of 2x. We're going to write out a bit of this series, just enough to do this problem. Since they are talking about a 5th degree approximation, that means that whatever the 5th degree term is, whatever x to the 5th term is in this series, we need to go one more term so that we can use alternating series error bound, because this relies on the next term. So let me write out my series for sine of 2x, at least for a little bit. So sine of 2x, sine of x, we're going to start there and then transform it into sine of 2x. The original sine of x series is just x minus x cubed over 3 factorial, and yes, you should have this memorized, plus x to the 5th over 5 factorial. And then they said they wanted the 5th degree approximation error bound, so we need one more term, which is going to be minus x to the 7th over 7 factorial. Okay, now we need to transform this thing. So sine of 2x, that's just plugging 2x in for all these x's. So x becomes 2x. X cubed is going to become 8x cubed, and then we'll have the minus and the 3 factorial still. This next term, we now are going to have 32x to the 5th over 5 factorial. Finally, we have minus, let's see, what's 2 to the 7th? That's 128. So 128x to the 7th over 7 factorial. All right, so the next step, they want us to use alternating series error bound. We need to justify that we can actually use it. Do we have an alternating series here? We do, and it's based off of sine, which is an alternating series, so it is just going to keep alternating. Sine of 2x just keeps alternating. Are we decreasing an absolute value to 0? Are these terms getting closer to 0 as we move along. Well, this one's a little bit tricky because although the factorials are growing, so is the exponent in the numerator. The key here is that we're plugging in a number that's between 0 and 1, 0.8. If I raise 0.8 to higher and higher powers, it gets smaller and smaller. So we have terms that are alternating, and they are indeed decreasing in absolute value to 0. This means, according to the alternating series error bound, that the error is going to be less than the absolute value of the next term. The next term bounds the total possible sum of all the other terms of the infinite series. Okay, so let's write an expression for the next term. Since this is a fifth degree approximation we're talking about, that means the next term is whatever we get when we plug 0.8 into this seventh power term. So I'm going to write error is going to be less than absolute value of 128.8 to the seventh over 7 factorial. And I got rid of this negative here because it's inside absolute value, so it's going to make it positive anyway. Now I'm going to use the calculator because they're talking about this value being less than 0.009, so I need to actually compute this with some accuracy. So plugging this expression in my fancy fraction mode here in my calculator, this comes out to about 0.005 and some change. So this is strictly less than 0.006, so I'm going to write that. And I also need to actually show that what I got is less than 0.009. Well, 0.006 is definitely less than 0.009, so I'm just going to write less than 0.009. And this last step, it seems kind of trivial, but this actually proves what they told us to prove. Without this last step, you don't get that last point, so make sure you include it. For this no calculator free response problem, f is a function having derivatives of all orders for all real numbers. That's code for, hey, we can make a series out of this. And we have values of f and its first 4 derivatives in this table. Not a whole lot of values, just at 0 and 1, but hopefully that'll be useful. So for the first part of the problem, they want the second degree Taylor polynomial about 0, and then they have to use this to approximate f of 0.2. So we have to build a Maclaurin series from scratch here. So my p sub 2, my second degree Taylor polynomial, the first thing in that series is going to be f of 0, f of the center, which is just 4 according to this table. Next, I need f prime of 0 times x, so that's going to be 5x. Next, I need f double prime of 0 over 2 factorial times x squared, so that's going to be negative 1 over 2 factorial with an x squared. And that's it. That's our second degree Taylor polynomial. We have to actually use this, though, to approximate f of 0.2. So I'm going to write f of 0.2 is approximately equal to p sub 2 of 0.2, which equals 4 plus 5 times 0.2 minus 0.2 squared over 2. Since I've got all constants here, I could actually just stop and call it a day. I don't have to simplify this. But if I did want to simplify, let's see, this is going to be 4 plus, this is going to be 1, so that's 5, which isn't horrible to deal with. This stuff over here, though, 0.2 squared, that's 0.04. Divided by 2, that's 0.02. So we have 5 minus 0.02, which is 4.98, if I really felt the need to simplify all that. For this next part of the problem, they're telling us g is basically just f of x cubed. They want the fifth degree Taylor polynomial for g prime, about x equals 0. Okay, well, let's write out the f function again, at least the approximation from part A. That again was 4 plus 5x minus x squared over 2, and I'm going to write approximately equals because this was just a polynomial version. Now to do g of x, which I need before I can get g prime of x, this is just going to be the f function with x cubed plugged in for all the x's. So this is going to still have a 4, but now we're going to have, this is going to be 5x cubed. This is going to be minus x cubed squared, which is x to the 6th, over 2. And now for the last part, they wanted g prime, and this needs to be a fifth degree Taylor polynomial. So this 4 gets differentiated away. Next we have 15x squared. And then finally, this just so happens to be, if I multiply 1/2 by 6, this is going to be minus 3x to the 5th power, which is a fifth degree Taylor polynomial. So we have done what the problem asked. On this problem, they want the third degree Taylor polynomial for f about x equals 1. So this is kind of interesting. We're changing the center to 1 instead of 0. so no longer a Maclaurin series. This is going to start with f of 1, which is just 8. So this is, I'm going to call this p sub 3 now. And then we're going to have f prime of 1 times x minus 1. F prime of 1 is 3, so this is going to be 3 parentheses x minus 1. Next, we're going to have an x minus 1 squared. And on the outside, we're going to have, let's see, our second derivative, negative 2 over 2 factorial times x minus 1 squared. And then finally, we're going to have our third derivative, 3 halves, times x minus 1 cubed, and we're going to have a 3 factorial in the denominator as well. On this part of the free response problem, they're saying it's known that the fourth derivative of x is less than or equal to 300 between 0 and 1.125. Third degree Taylor polynomial about x equals 1 is used to approximate f of 1.1. Okay. They want us to use the Lagrange error bound along with information about the fourth derivative to find an upper bound on the error of the approximation. So they said Lagrange, so we go straight to our Lagrange formula. So we're going to say error is less than or equal to, this is not alternating series, so it's less than or equal to big fraction. And in the numerator, I need the max derivative over the interval in question. Now, the interval that we're using for our max, for our derivative, it's always going to be the interval between the center of the polynomial and the x value you're approximating at. So our center, they said, was x equals 1. We're approximating at x equals 1.1. So we have a max then between 1 and 1.1. Now, which derivative are we using? Well, if it's the third degree Taylor polynomial, we need the fourth derivative of x. And, I mean, they told us, hey, use the fourth derivative, but this just confirms it because we had third degree. So if it's fourth derivative, it's fourth everything else. So we have 4 factorial here, and we're going to have x minus 1 to the fourth. Now, I don't need the absolute value in this instance here because I have an even power. So at this point, I need to figure out my max derivative for the fourth derivative of x. In general, there's 4 ways you can figure this out in a Lagrange problem. One way is you might be able to figure it out from a graph if they gave you one. If you're using a graph, just pick a safe upper bound and use that. Or if they gave you the actual function for f, you could take derivatives until you get to the fourth derivative and then pick an x that maximizes that derivative. Or you might have a table like they gave us up here. But if you're trying to figure out the maximum value in a table, you need to have information about whether these things are increasing or decreasing. I mean, for example, they told us that at 1, the fourth derivative is 2/5. But that doesn't tell us that this is the biggest that derivative is ever going to get. So we would need more information in order to write 2/5 or really anything based off this table. The only other way you know what the max derivative is if they give it to you in the problem. This particular problem, they gave it to us. They said the derivative, the fourth derivative, is always less than or equal to 300 on the interval from 0 to 1.125. Well, the interval from 0 to 1.125 includes this interval, and I actually should make that a bracket there. But in any case, that includes this interval from 1 to 1.1. So that means that this whole max fourth derivative expression, we can just write 300 up there. So I've got 300 up there. I've got 1.1 minus 1 to the fourth. And this is my upper bound on my error of approximation. Now, if I wanted to, I could simplify this, but it's a no calculator question, so be careful doing this. So this 1.1 minus 1, that's 0.1. If I raise that to the fourth, I've essentially got 1/10,000th. So I've got 300 in the numerator and 4 factorial and 10,000 in the denominator. So I can do a little bit of canceling here. 2 of these zeros are going to cancel, so this is really 3 over 100. 4 factorial is 24, so we've got 3 over 2400, which I could reduce to 1 over 800. Again, wasn't necessary, but I could have if I wanted to.